So, in the first lecture of concentration inequalities, we talked a bit about how a sum of IID random variables could decay. And we saw that if it has an exponential moment which is finite for some theta, then it has an exponentially fast decay of deviation probabilities. In this talk, we're gonna refine that result a bit, and we're gonna try to obtain uh, bounds which are closer to optimal. And this is called large deviation principle. So this talk we're gonna start talking about large deviations. And before, let's just recap what we saw in the last lecture. So suppose we have random variable x1, x2, and so on and so forth, which are IID, and say the expectation of e to the theta x1 is finite for some theta. In particular, this let's suppose they are non-negative, for example. So we now know that the expectation of x1 is finite. So let's call this m. What we studied before was the sum Sn of xi, and we try to understand the probability that Sn is larger than some x times n, where x is above the expectation. So what's the probability that we deviate from the expectation by more than x? And what we saw is that this probability decays with some exponential rate in n, if we have this moment condition here. And in some cases, in actually most cases, it also has a lower bound of the same type. So this is the type of behavior we expect for this sum of IID random variables. So it should have an exponentially small probability of deviating from the mean. But in some cases, not all, but in some cases, we also have a lower bound of the same order. And when we are talking about large deviation principles, we really want to get this constant right. So up to now, we just said there is a constant such that. And what we're going to try now is to get the precise constant. And this has several very important applications because in several contexts, and especially in statistical mechanics, this constant, when it's correct, when it's essentially the same on the left and the right, essentially, it means that it has a very important physical meaning, this constant. So that's why it's so important to understand what its value. And in several situations, we know its value exactly. So this is what we're going to study in large deviations. And I'm going to start recalling a little bit what we did in the last lecture when we obtained this Roth bound here. And what we did was to use an exponential moment of the following type. We looked at the expectation of e to the theta x, and this we defined as Lx of theta. It's a Laplace transform, and this, as soon as this is finite for some theta, this is going to be finite for a whole interval. So suppose that it's finite at theta 0, so it's going to be finite for every value until theta 0. It's not difficult to see. So at 0, this function is 1. because we are taking the expectation of 1. And then if it's finite for some theta, it's also finite in the interval. So this was a very important function in our last lecture. And what we're going to do is to define another function, which is also important for large deviations principle, but we're going to motivate this in a slow fashion. So first, let's recall what was the strategy of the proof. The probability that Sn is larger or equal than, let's write it like this, xn, with x larger than the expectation of x1. This could be written exactly as the probability that e to the theta Sn is bigger or equal than e to the theta xn. And now we use Markov's inequality to obtain a bound of the following type. You can see here that exponential moments are already appearing. But the nice advantage here is that Sn is a sum. Exponentials of sums become products of exponentials. And these are independent random variables. So we can break this into a product outside. And note here that now it's an IID sequence, so this becomes just a product. Sorry, becomes just a power. So this is going to be, actually just write it as the Laplace transform of x1 to the power n e to the minus theta xn. So this inequality holds for every theta. So what we're obtaining is a general bound that we should optimize. In the first lecture, what we did was just to take some small enough theta such that this term loses to this term that may grow loses to this term that decays. But now we're going to try something even more precise. So we're going to write this in a strange way. We're going to take exponential and the logarithm. So here we have log of Lx1 theta. Put in a bracket here. Minus, now the log of the exponential is just the argument. And outside we have n. I'm going to revert the order of this because I want to make it look like it's something decaying. I want to have the feeling that this is going to 0, so I'm going to put a minus here, theta x minus log of the Laplace transform times n. And note that this holds true for every theta larger or equal to 0. In particular, we can take the probability that we're trying to estimate is smaller or equal than the infimum over all non-negative thetas of the same thing, exponential of something. And the exponential function is an increasing function, so we can take the infimum inside, and since there's a minus sign here, it becomes a supremum. So now it's the exponential of minus the supremum over theta larger or equal to 0 of theta x minus log Lx of theta n. So let's just recap what we just did. We want to estimate this. We use exponential moments and we optimize over theta. We use, of course, the independence, the fact that exponentials break into products, and we optimize over theta to obtain this last inequality. But I don't want to stay in this last inequality for long. I just want to focus a little bit on this term here. you remember that we are trying to obtain the coefficient. So this is going to be an interesting candidate for a coefficient, right? So we get e to the minus constant times n, and this constant is something that we're going to give it a name now. We're going to call this the rate function. Because it somehow measures the rate of decay. So the rate function for some measure is just going to be the supremum. Oops, sorry. It has an argument at x, and it's going to be the supremum over theta. And you see that before we had theta bigger or equal to 0. Now I'm not going to make this restriction. I'm just going to take any theta, the supremum of the function theta x minus the logarithm of the Laplace transform of mu in the point theta. So this is a candidate we have for the decay, the exponential decay, although we have a small difference here that we were proving this for theta larger or equal to 0, and now I'm defining the supremum to be for every theta, but this is going to be clear soon what we mean by this. So now we're going to state a theorem that relates to our objective of obtaining sharp bounds, and essentially already proved the theorem, right? This is a theorem that is due to Cramer and Chernoff. Although we are only proving the first part. So this is part 1. And it's perhaps the most important large deviations theorem, although it has been followed by a huge theory that is very interesting on its own. It starts with a sequence of random variables, just like we did before, which are IID. We're gonna denote its distribution by mu. We're gonna write m for its expectation and define Sn to be the sum of xi, just like we did before. So we already have defined the Laplace transform and the rate function. I'm not going to redefine them here. I'm just going to state the main result, which is, by the way, let us observe that the Laplace transform is always defined if you think of it as something belongs to 0 infinity. So it's the expectation of an exponential. So it's always well defined, although it could be infinite. And also the rate function is always well defined, or it could be infinity as well. And it could be 0. So what the theorem states is first that for x larger or equal to m, so if we are above the expectation of x1, then the probability that the sum is larger or equal than x decays like e to the minus I mu of x times n. And for the second part, for x smaller or equal to m, this probability becomes, and the probability that you are below x has the same decay. So this is the statement of the theorem. We are only proving part 1. The part 2 has to do with a corresponding lower bound, and we're going to see this in a later lecture. But what's interesting is that this gives a very nice representation of the decay. And I'm going to just do some simple example of the theorem before proving it. So this example is gonna be inspired by the coin toss. So we have a random variable x1, which has distribution delta of -1 plus delta 1 over 2. So it has probability 1/2 of being either 1 or -1. So what is the Laplace transform of x? This is going to be an expectation taking only two values. So it's going to be 1/2 with probability 1/2. The exponential inside the expectation is going to take this value times 1. And with probability 1/2, it's going to take this value. So this is exactly the hyperbolic cosine of theta. And if we plot it, this is what we get. It has exponential growth in both directions, plus and minus infinity. It hits 1 here, as always, because the expectation of e to the 0 is 1. It's a convex function going to infinity in both directions. And if you remember the rate function, we are looking into the logarithm of this function with a minus sign. So let us plot what this log is. So at 0, its value is 0 because it's log of 1. The function that we started with is always bigger or equal to 1. So the logarithm is going to be bigger or equal to 0, but we're taking the minus sign here. So this function is going to look like this. And you see, this is growing exponentially. When we take the logarithm, when we go in this direction, this term is not important. It's essentially behaving like e to the theta. And the logarithm is essentially behaving like theta, minus theta. So asymptotically, this is going to be like a line. Okay? This is going to be like a line asymptotically, both here and here. So no longer exponential growth. We killed the exponential growth with the logarithm. And now we are trying to visualize what this definition is. So we have this supremum over theta of theta x minus this log. So intuitively speaking, we fix some x. So for example, x could be a 1, for example. So we have this line here. And this line represents this function, theta x. Here we have theta, right? And here we have minus log of L mu to the theta. So here, this black function is this, and the green line is this. And we're, the black is including the minus sign. So we are summing the two and maximizing. You see that the maximum is gonna be when obtained when the curve is further away from the line. Here perhaps. So this is gonna be where the maximum is attained. Because when we sum these two, we're gonna maximize when the derivative is the same. So if we shift this, just like here, so sorry, I did something wrong here. So when we sum these two functions, what will be obtained is a red function like this. And the maximum of the sum is going to be attained exactly when the derivatives are the same, are the opposite, sorry. One is minus the other. And another way to see this is to draw minus the function here. So this is the function that we should be looking at. And the maximum is going to be attained when this difference is higher, because it's going to be exactly when the two have the same derivative. So the maximum is going to be attained in this theta star here, and the value of the maximum is going to be just the shifted version. If we translate this line to here, this is going to be the maximum. So one way to see, so this is I mu of x. So one way to see this is to do to take the function that you had originally. So I have a function like this, and we come with lines of various angles, and the point where this line, so the angle of the line is x, and the point that this line hits the y-axis is I of x. So you see this is a kind of dual of the optimization problem. And there is a long study about this transformation. This is called the Legendre transform of this. But one important thing to observe in this specific case of Bernoulli random variables is, first, this is always bigger or equal to 0. Actually, this is general. The Legendre transform of the rate function is always non-negative. Its value, so now I'm trying to plot here not theta but x and I mu of x. So at value 0, we are talking about a flat line here. Sorry, flat line here. So this value is going to be 0. And as soon as you move a little bit, it moves up in both directions. So I is convex, and when you hit the value 1 or minus 1, you saturate. When this line becomes parallel to the asymptote of this minus log here, this thing blows up. So it goes from some finite value to infinite. As I said, the rate function can be infinite. And the same happens here. I'm not going to pay much attention to the fact that it can be infinite for now, but just the fact that it's convex here and the value is 0 at 0, and by the way, this is 0, which is exactly the expectation of x1. So when we are trying to see the average S n over n be larger or equal to x, this is the exponential decay. When you're trying to see the probability that S n over n is smaller or equal to some other x here, this is the exponential decay. So you can see exactly what the exponential decay is by looking at this picture. You just have to take care that the exponential decay refers to being bigger than x above the expectation or smaller than x below the expectation. So this is the region that has this exponential decay, and this is the region that has this exponential decay. So these are calculations that we're not doing here, but you can explicitly calculate the rate function. So you can get an explicit value for this exponential decay the theorem is stating. And now we're going to make some very simple observations, and the proof of the theorem is going to go through very easily. So the first observation is related to linear transformations of the variable x. So imagine that y is ax minus b or plus b with some non-zero coefficient a. What is the Laplace transform of y? So this by definition is e to the theta exponential expectation of e to the theta y. So the b will go out because it's a sum, it will become a product. Expectation of a constant times something is the constant times the expectation of this something. So we can write this as, so this is just a number times the Laplace transform of x at the point a theta. So if we look at the rate function of y, rate function of y, sometimes I'll write here the distribution, sometimes the random variable. This is the supremum, as we saw, of theta x minus log. And now we're going to write the Laplace transform with this formula we have. Log of this times log of that is just the sum. A theta. So it's the supremum of this. So this stays the same. Here we have theta b. So I'm going to put theta here minus the log of the Laplace transform of x at the point a theta. And what's the advantage of writing it like this? If we write, if we do the transformation a theta to eta, then this, because a is non-zero, this supremum is the same if we take it over theta or over eta. And here we have eta times x minus b over a, right? Eta over a is theta minus log of Lx at eta. Great, so this is just the rate function of x, right? Taking the rate function of x at a strange point. We're no longer looking at the point x, but looking at the point x minus b over a. So there is a simple transformation. When we do a linear transformation in a random variable, we do a linear transformation on the rate function. So for example, if we just sum, forget the a now, imagine that a is 1. If we just sum some variable, some constant b to some variable x, we're going to subtract b in the rate function, so we're going to shift it to the right. So for example, here, if instead of having a random variable like delta of minus 1 plus delta of 1 over 2, we had a random variable that was delta of 0 plus delta of 2 over 2. So something that is, so this is, let's call this y. Y is x plus 1 that has distribution written like this. What would happen with the rate function would be that it would get a shift to the right, like this. And here the average would be, the mean would be 1. This is always the expectation. So we can understand how linear transformations of the random variable act on the rate function. Now we are ready to give the full proof of the first part of Cramer's theorem. So proof of Cramer-Shanov theorem. So first, observe that we can suppose without loss of generality that m equals 0. Why? Because if m is not 0, we can just subtract m, and we use this formula here to show that the theorem doesn't change. So we obtain the same theorem with m equals 0. So this is something that you can easily check. So now we are going to do the calculation that we already did before, like the probability that, so now we have x larger or equal than m, which is by the way 0, and we are looking at the probability that Sn is larger or equal than x times n. This we already saw is smaller or equal to the exponential of minus the supremum, but here we had to do over theta bigger or equal to 0, unhappily. So we don't get the rate function that we need. Minus log of the Laplace transform of x. So this is almost the rate function, not the rate function. Now what we're going to do is to study what happens for theta smaller or equal to 0. So for theta smaller or equal to 0, the Laplace transform is, as usual, the expectation of e to the theta x by Jensen's inequality. This is larger or equal than the exponential of the expectation. But now the expectation of x is 0. We are assuming that it has 0 expectation. So this is 1. And what we are taking the supremum here, theta x minus log of the Laplace transform, is going to be smaller or equal, because the larger or equal with this minus sign becomes smaller or equal, to the log of 1, which is 0. And this, remember that theta is negative and x is non-negative, right here. So this is smaller or equal than 0. So theta is non-positive, x is non-negative, so this is smaller or equal to 0, which is, by the way, I mu of 0. So in the end, we are showing that the supremum over theta larger or equal to 0 is the supremum over all theta, because the negative thetas gives some value for the argument of the supremum, which is smaller than the value at 0. So we are not getting any advantage by changing this to supremum over theta. So after this observation, we see that this is smaller or equal than e to the minus the rate function at x times n, as desired. So this finished the proof of the first part of Cramer's theorem, and it looks like what we did in the first class. We're just optimizing over theta and doing some observations about how we optimize of theta. But this is going to become very surprising when we see the second part of the theorem, where we try to prove an inequality in the other direction. So that's going to be a very nice part.